Hello and welcome to this module, Properties of Group Homomorphism and Isomorphism. In this section, we will give a brief introduction of homomorphism and isomorphism. Together with the introduction, we will teach some of its properties with examples. This section will give a brief introduction of homomorphism and isomorphism. Together with the introduction, we will teach some of its properties with examples. It will be very useful to the upcoming sections. Let's start with the definitions. The definition of group homomorphism. A homomorphism phi from a group G to G bar is a mapping from G into G bar that preserves the group operation. That is, phi of AB is equal to phi of A times phi of B for all A comma B in G. One other definition is kernel of a homomorphism. The kernel of a homomorphism phi from a group G to a group H with identity E is the set of all x belongs to G such that phi of x is equal to E. The kernel of phi is denoted by KER phi, also denoted as kernel phi. For a brief understanding, let us see some examples. Consider the function phi of x is equal to x squared from r star to r star under multiplication to r star under multiplication. R star represents the set of all non-zero real numbers. This function is a homomorphism because phi of AB is equal to AB squared, that is equal to A squared B squared, which is equal to phi of A times phi of B. This satisfies the condition of a homomorphism. Now let us calculate the kernel of this homomorphism. We have to calculate those elements which are mapped onto the identity element of R comma star. We know that because it is a multiplicative group, the identity element of R star comma dot is 1. Therefore, we need to find the elements which are mapped onto 1. Clearly, only the elements 1 and minus 1 are mapped onto R star comma dot. So, the kernel of phi is 1 comma minus 1. Let us go to example number 2. Define the mapping phi from R star to R star by phi of x is equal to modulus x. Here, let us check this function for homomorphism. Clearly, it is a homomorphism because phi of AB is equal to phi of A times phi of B. Now, let us calculate the kernel. Since the function is phi of x is equal to modulus x, clearly kernel phi is 1 comma minus 1 since the identity element of phi is 1, where 1 belongs to R star, the codomain. So, kernel phi is those elements which are mapped onto the multiplicative identity of R star here, and therefore, kernel phi is equal to 1 comma minus 1. Let us see one more example. Let us define a mapping phi. Now, this particular function is defined by phi of m is equal to m mod n. Here, let us check this function for homomorphism. This is true because the remainder of dividing a plus b by n is the same as dividing the remainder a by n and b by n. So, this is clearly phi of a. Now, let us calculate the kernel of this particular function phi. Now, kernel phi is the set of all elements which are mapped onto the additive identity of Zn comma plus. Now, we know that the function is m mod n, and therefore, only those elements with remainder 0 can belong to the kernel of this function. Hence, clearly these elements, the multiples of n, are going to be belonging to the kernel of this function. Let us see one more example. Consider the homomorphism phi of x is equal to x squared from R to R. The real numbers and addition is itself not a homomorphism, because phi of a plus b is equal to phi of a plus b the whole squared, that is a squared plus b squared plus 2ab. But phi of a plus phi of b is equal to a squared plus b squared. Clearly, phi of a plus b is not equal to phi of a plus phi of b. Hence, this particular function is not a homomorphism. We need the upcoming results to prove some properties of homomorphism. So, let us see the result first. Result: let G be a group and let A be an element of an order n in G. If A power k is equal to E, then n divides k. Now, we shall see the properties of homomorphism. Let phi be a homomorphism from a group G to a G bar, and let G be an element of G. Then there are certain properties that I will write on the board now. Phi carries the identity element of G into G bar. The second property is phi of G power n is equal to phi of G the whole power n for all n belonging to the set of integers. If the order of G is finite, then the order of phi of G divides order of G. Number 4, kernel phi is a subgroup of G. And fifth property, phi of A equal to phi of B if and only if A kernel phi is equal to B kernel phi. The last property, if phi of G is equal to G dash, then phi inverse of G dash is equal to the set of all x belongs to G such that phi of x is equal to G dash, and this is also equal to G kernel phi. Now, let us see the proof of the first property. Let us denote the identity of G by E and the identity in G bar by E bar. Then we know that since E is equal to E times E, phi of E times phi of E is equal to phi of EE. We are actually applying the phi function on this particular expression. Therefore, we have phi of E times E is the same as phi of E, and that is nothing but E bar times phi of E. Now, phi of E times phi of E is equal to E bar times phi of E. Since phi of E belongs to G bar, we have phi of E is equal to E bar times phi of E. We have to cancel on both sides. We cancel phi of E on both sides. We get E bar is equal to phi of E, and therefore 1 is proved. The second property, if n is negative and then minus n is positive. So, n is less than 0, then minus n is greater than 0. Now, from the first property, E bar is equal to phi of E. Since we know that identities are mapped onto identities, that is equal to phi of g power n times g power minus n. We know that these two will cancel each other, and therefore we have taken a random element g times a random element g power minus n. Now phi of g power n is times phi of g power minus n. This is due to the property of homomorphism. That is equal to phi of g power n times phi of g the whole power minus n. We multiply on both sides on the right by phi of g times the whole power n. When we do so, E times phi of g the whole power n is equal to phi of g power n, phi of g power minus n, we have written it as it is, and then phi of g the whole power n is here. These terms get cancelled, these two get cancelled, and we are left with E bar dot phi of g the whole power n is equal to phi of g the whole power n. That is, phi of g the whole power n is equal to phi of g power n. Hence, the property number 2 is proved. To prove property number 3, notice that the properties 1 and 2 together with g power n is equal to E implies E is equal to phi of E equals phi of g power n equals phi of g the whole power n. So, by the previous result, we get that phi of g divides n. Next, by property 1, we know that kernel phi is not empty. So, to prove property number 4, we assume that A and B belong to kernel phi, and we show that AB inverse belongs to kernel phi. By doing so, we will be able to prove that kernel phi is the subgroup. Now, let us see the fourth property. We have to prove that kernel phi is a subgroup of G. Let A comma B belongs to kernel phi. We know that kernel phi consists of the set of elements which are mapped onto the identity element of G bar. Now, we have to prove that AB inverse belongs to kernel phi. We know that if we prove that AB inverse belongs to kernel phi, then kernel phi becomes a subgroup of G. Now, phi of A is equal to E. Why is this possible? Because A and B belongs to kernel phi, and therefore phi of B also is equal to E. Now, we need to calculate phi of AB inverse. Phi of AB inverse is equal to phi of A times phi of B inverse, that is equal to phi of A times phi of B the whole inverse. This is phi of A is mapped onto E, and phi of B inverse is mapped onto E inverse, which is the same as E, and therefore the product of these two identities is equal to E. Now, phi of AB inverse is equal to E implies that AB inverse belongs to kernel phi. Hence, kernel phi is a subgroup. The fifth property, let phi of A is equal to phi of B. We are supposed to prove that B kernel phi is equal to A times kernel phi. E is equal to phi of B the whole inverse times phi of A, that is equal to phi of B inverse times phi of A, that is phi of B inverse A is equal to E. Therefore, B inverse A belongs to kernel phi, and you bring this to this side, so it becomes B kernel phi is equal to A kernel phi. We know that this is possible because AH is equal to BH if and only if A inverse B belongs to H. We shall now prove property number 6. We are supposed to prove that G kernel phi equals phi inverse of G dash. We shall go about this by proving that one is a subset of the other, and then conversely. So, let us first prove that G kernel phi is a subset of phi inverse of G dash. To do this, we have to take an element x from phi inverse of G dash, and we take that phi of x is equal to G dash. This is because phi inverse goes here, and therefore phi of x is equal to G dash. Then phi of G is equal to phi of x, and therefore by the fifth property, G kernel phi is equal to x kernel phi, and therefore x belongs to G kernel phi. We have now proved that phi inverse of G dash is a subset of G kernel phi. Take this as equation number A. Now, let K belongs to kernel phi. We are doing the converse part now. So, phi of Gk is equal to phi of G times phi of K, that is equal to G dash times E. This is nothing but G dash. Now, Gk, take the phi on the right hand side, it becomes Gk belongs to phi inverse of G dash. Now, this is Gk belongs to G kernel phi, and therefore G kernel phi is now a subset of phi inverse G dash. From A and B, it is clear that G kernel phi is equal to phi inverse of G dash. Hence, property 6 is proved. Now, we shall verify some of the properties that we have discussed earlier. Let us consider this example. Let f be a function from z12 to z12. Z is a integer group of modulo 12, and we have defined this function to be f of x is equal to 3x. Now, let us verify the homomorphism property. F of a plus b is equal to 3 times a plus b, that is equal to 3a plus 3b, which is equal to f of a plus f of b, and therefore homomorphism holds. Kernel of this function is 0, 4 and 8. Because 0 mod 12 is 0, 4 mod 12 is also 0, and therefore 8 mod 12 is also 0, because it is a 12 modulo group, and therefore the kernel is 0, 4 and 8. We can clearly see that because f of x is equal to 3x, f is a 3 to 1 mapping. This is because of property 5. Now, since f of 2 is equal to 6, because 3 times 2 is 6, by property 6, which is f inverse of G dash is equal to G kernel phi, f inverse of 6 is equal to 2 plus kernel f, that is 2 plus 0, 4 and 8, which is 2, 6 and 10. We know that the group generated by 2 is cyclic, and we can see that the group generated by f of 2 is also cyclic because it maps onto 0, 6. Now, the order of 2 is 6. You can clearly see that if you add 2 6 times, it is equal to 0, which is the additive identity of this group Z12. Therefore, cardinality of the order of f of 2 is equal to order of 6, but 6 if you add 2 times, you get 12, which is equal to the additive identity 0 of Z12. Therefore, order of 6 is equal to 2. Clearly, the order of f of 2 divides the order of 2. We know that 2 divides 6, and therefore the order of f of 2 divides order of 2, and hence property 3 of the theorem holds. Now, let us take k bar to be 0, 6. Now, f inverse of k is equal to 0, 2, 4, 6, 8 and 10. So, property 6 of theorem also holds, and because f inverse of G dash is equal to G kernel f. So, we have verified some of the properties of the previous theorem. We shall now move on to some more other theorems based on the kernel. Theorem: a homomorphism phi from G to H is injective if and only if kernel phi is equal to E, the identity element. Injective property is 1-1 property. It is also called 1-1 property. Now, we will assume that phi is injective, and we shall prove that this is true. Let us assume that phi is injective. Let us assume some k to belong to kernel phi. So, obviously, phi of x is equal to E dash being the identity element of H, that is equal to phi of E. This is because identity elements are mapped onto identity elements by the property 1. Therefore, from this we can say that x is equal to E. Therefore, kernel phi is equal to E, and hence one part of the theorem is true. We have proved one part. The second part, conversely assuming kernel phi is equal to E, we are supposed to prove that the function phi is injective. Phi of x is equal to phi of y implies that phi of x y inverse, take this on the other side. So, phi of x y inverse is equal to phi of x into phi of y inverse. This is true because phi is a homomorphism, and this is equal to E dash, and therefore, we have now proved that phi is injective. So, this is the end of this theorem. Now, we will see the next theorem. Let phi from G to H be a homomorphism of groups. Then kernel phi is a subgroup of G, and image phi is also a subgroup of H. So, this is the function phi mapping the group G onto H. Now, we have to prove that kernel phi, which is a subgroup of G, and image phi, which is a subgroup of H, are both non-empty, and they are subgroups of H. Kernel phi and image phi are both non-empty. So, let us take two elements A, B in kernel phi. So, we know that we have to prove that AB inverse is also in kernel phi. So, phi of AB inverse is equal to phi of A times phi of B inverse, that is equal to E dash times E dash, which is equal to E dash, where E dash is the identity of H. Hence, AB inverse belongs to kernel phi, which implies that kernel phi is a subgroup of G. Similarly, we have to prove that the image phi, which is actually here, is a subgroup of H. Let alpha comma beta be any two elements in image phi. Then alpha is equal to some phi of x from here. So, some phi of x is equal to alpha here. And similarly, beta in this H is equal to some phi of y, where x and y are inside G. Then alpha beta inverse is equal to phi of x times phi of y the whole inverse, that is equal to phi of xy inverse, which belongs to image phi, and therefore image phi is also a subgroup of H. Now, we shall define what is a group isomorphism. We have discussed the properties of homomorphism, we have discussed the theorems related to the kernel. Now, we shall go on to isomorphism. An isomorphism phi from G to G bar is a one-to-one mapping of function that preserves the group operation. So, which means that it is homomorphism property plus an injective property or the 1-1 mapping. So, if phi is a function from G to G bar and it is an isomorphism, we say that G is isomorphic to G bar. This is the notation we use. We shall now see the properties of group isomorphism. Some of these properties are going to be repetitions of the properties that we saw in group homomorphism. Let us go on to the properties. Suppose that phi is an isomorphism from a group G onto a group G bar, then property number 1, phi carries the identity of G into the identity of G bar. Property number 2, for every integer n and for every group element A in G, phi of A par n is equal to phi of A the whole par n. Property number 3, for any elements A and B in G, A and B commute if and only if phi of A and phi of B commute. Property number 4, G is equal to the set generated by A if and only if G bar is equal to the set generated by phi of A. Property number 5, the order of A is equal to the order of phi of A for all A in G, because isomorphisms preserve orders. Property number 6, for a fixed integer k and a fixed group element B in G, the equation A par k is equal to B has the same number of solutions in G as does the equation x par k is equal to phi of B in G bar. Property number 7, if G is finite, then G and G bar have exactly the same number of elements of every order. Let us see some theorems. Theorem: every cyclic group is isomorphic to Z or to Z by n for some n belongs to the set of natural numbers n. Proof: if G is equal to A, the set generated by A, is an infinite cyclic group, consider the mapping phi from Z to G given by phi of I is equal to A par I. It is clear that phi is a surjective homomorphism. Moreover, I is not equal to J implies A par I is not equal to A par J, for otherwise A would be of finite order. Hence, phi is injective. Therefore, phi is an isomorphism. Next, suppose that G is equal to the set generated by A is a cyclic group of finite order n. Then G is equal to E, A squared so on up to A par n minus 1 and order of A is equal to n. Consider the mapping phi from Z by n to G given by phi of I bar is equal to A par I. Phi is well defined and also injective. For let I bar comma J bar belong to Z by n, then I bar equal to J bar implies that n divides I minus J, which implies A par I minus J is equal to E, which in turn implies A par I is equal to A par J. The following steps re-imply themselves also. Clearly, phi is surjective. Further, phi of I bar plus J bar is equal to phi of I plus J the whole bar, which is equal to A par I plus J, which is equal to A par I A par j. Hence, phi is an homomorphism. Until now, we saw that if a group is cyclic, then we can define an isomorphism. But if not, then the next theorem will give a clarification. The most important theorem is Cayley's theorem. We shall now see Cayley's theorem. Cayley's theorem says that every group is isomorphic to a group of permutations. The proof: let G be a group. For any A belonging to G, the mapping Fa from G to G is given by Fa of x is equal to Ax for all x belongs to G. We have to prove that it is a bijection. So, Ax is equal to Ax dash, which implies x is equal to x dash. And if we take any y is equal to Fa of A inverse of y for all A, B, x belonging to G. Therefore, y belongs to G, and hence we can say that it is a surjection. Fa of B is equal to AB of x, that is Fa of Bx, Fa of Fb of x. So, we are clubbing Bx to be Fb of x. Then finally, we are left with Fa Fb of x, and therefore, phi of AB is equal to phi of A times phi of B, and therefore, phi is a homomorphism and the image phi is a subgroup of Sg, and hence phi of A is equal to phi of B implies Ax is equal to Bx for all x belongs to G, which implies A is equal to B, and therefore, phi is an injective homomorphism. Any injective homomorphism is an isomorphism, and therefore, phi is an isomorphism. So, we have now proved that G is isomorphic to a subgroup of Sg. Hence, phi of AB is equal to phi of A times phi of B. We have now proved that phi is a homomorphism, and we know that image phi is a subgroup of Sg, Sg being the group of permutations. Therefore, phi of A is equal to phi of B implies Ax is equal to Bx for all x belongs to G, which implies A equals B. This proves that phi is an injective homomorphism. An injective homomorphism is an isomorphism. Therefore, G is isomorphic to a subgroup of Sg. Until now, we saw about homomorphism and isomorphism, but there is also one more morphism, which is the automorphism. Let us see the definition now. The definition of automorphism: an isomorphism from a group G onto itself is called an automorphism of G. Let us see some examples of automorphism. Example 1, let R squared is equal to the set A comma B such that A comma B belongs to R. Then f of A comma B equals to B comma A is an automorphism of the group R squared under component wise addition. Geometrically, f reflects each point in the plane across the line y equals x. More generally, any reflection across a line passing through the origin or any rotation of the plane about the origin is an automorphism of R squared. Let us see some results of automorphism. Result 1, let G be a finite abelian group of order n and let M be a positive integer prime to n. Then the mapping sigma from x to x bar m is an automorphism of G. Proof: let m comma n equals to 1. That is, m and n are relatively prime. This implies that there exist integers u and v such that mu plus nv is equal to 1, which implies for all x belongs to G, x is equal to x bar mu plus vn, that is equal to x bar mu times x bar vn, that is equal to x bar um, since order of G is equal to n. Now, for all x belongs to G, x is equal to x bar u the whole times m, which implies that sigma is onto. Further, x bar m equals E implies that x bar mu is equal to E, which implies x is equal to E, showing that sigma is 1 to 1. That is, sigma is a homomorphism following the fact that G is abelian. Hence, sigma is an automorphism of G. The next result: if G is a finite cyclic group of order n, then the mapping sigma from A to A bar m is an automorphism of G if and only if m comma n is equal to 1. And the group of automorphisms of G is phi of n, where phi is Euler's function. Proof: if m comma n is equal to 1, then it has been shown in previous results that sigma is an automorphism. So, let us assume now that sigma is an automorphism. then the order of sigma of A is equal to A power m. It is the same as that of A, which is n. Further, if m comma n is equal to d, then A power m the whole power n by d is equal to A power n the whole power m by d, that is equal to E. Thus, the order of A power m divides n by d, that is n divides n by d. Hence, d is equal to 1, which implies sigma is an automorphism if and only if m comma n is equal to 1. Let G is equal to A, the set generated by A, be a finite cyclic group of order n, and sigma belongs to the automorphism group of G. Since sigma of A dash is equal to sigma of A the whole dash for each integer I, sigma is completely known if we know sigma of A. Now, let sigma of A is equal to A power m, where m is less than or equal to n, and we have m comma n is equal to 1. Thus, each sigma determines a unique integer m less than and prime to n, and conversely, which implies the number of group automorphism of G is phi of n. Now, let us see the inner automorphism induced by A. The definition: let G be a group and let A belongs to G. The function phi A defined by phi A of x is equal to Ax A inverse for all x in G is called the inner automorphism of G induced by A. An example of an inner automorphism is the action of the inner automorphism of D4 induced by R90 is given in the following table: x to R90 x R90 inverse, R0 goes to R90 R0 R90 inverse, that is equal to R0. R90 goes to R90 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 inverse, that is equal to R90. R180 goes to R90 R180 R90 inverse, that is equal to R180. R270 goes to R90 R270 R90 inverse, that is equal to R270. The H is mapped to R90 H R90 inverse, that is equal to V, and V is mapped to R90 V R90 inverse, that is equal to H. D is mapped to R90 D R90 inverse, that is equal to D dash, and D dash is mapped to R90 D dash R90 inverse, that is equal to D. Let us verify the set of all automorphisms of G is a group or not under composition map. Result: the set odd G of all automorphisms of a group G is a group under composition of mappings. Proof: clearly odd G is non-empty. Let sigma comma tau belong to AUTG, or also denoted as odd G. Then for all x comma y belongs to G, sigma times tau of x y is equal to sigma of tau x tau y, that is equal to sigma tau of x sigma tau of y. Hence, sigma tau belongs to odd G. Again, sigma of sigma inverse of x sigma inverse of y is equal to sigma sigma inverse of x sigma sigma inverse of y, that is equal to xy. Hence, sigma inverse of x times sigma inverse of y is equal to sigma inverse of xy. Therefore, sigma inverse belongs to odd G. This proves that odd G is a subgroup of the symmetric group SG, and hence itself a group. By using automorphism and inner automorphism, we can say that a group is complete or not. In this module, we have seen about homomorphism, isomorphism, automorphism. We have seen some of its properties together with some examples. I hope it was useful to you. Thank you.